Hello students, in the second part of this video let us continue. So the evolutionary process gene flow is nothing but migration, the movement of population from one place to another, which leads to intermingling among different populations. Okay, so this is a very common process. For example, you must have seen migration could be due to any reason. It could be war, it could be calamity, it could be displacement, or any other kind. For example, migration could be for job also, or any other reason. Okay, for marriage also, different leading to gene flow. Okay, so gene flow is very important. In case of gene, you have possibly from the population. It could be a part of population, this small population which is moving and migrating. For example, many specific populations migrated from Europe to America, leading to their own particular characteristic being taken into a separate different population. And in many cases it led to interbreeding and inbreeding also. So there would be many different characteristics leading to change in the gene frequency and the allele frequency. And the last process is natural selection. Natural selection. This is a very common, very famous theory given by Charles Darwin in his theory of evolution. So natural selection, as the name suggests, it is a natural selection of traits which are favorable for survival and they will move to next generation. Okay, so this is called natural selection. There are few factors regarding natural selection which you should know. One is variation. There should be variation in characteristics. For example, there could be some people who are tall. There could be some people who are having different kind of characteristic, having good physique. Okay, this could be, and other people in the population may not have that characteristic, so that creates a variation among the characteristics. Another is heredity. For natural selection to happen, there should be heredity of that character. It should be transferring from one generation to another. Not just very important, this heredity will not apply to all. It is a very common thing to understand and think that heredity will be applicable to all, but no. Many people in the population may not be able to reproduce. So in this case, it will not be applicable, but where heredity is approachable and eligible, then only a natural selection will occur. And finally, there will be another characteristic of natural selection, which is survival. It should be survival oriented. It should be advantageous characteristic. Then only it will be naturally selected. Okay, so these are the few evolutionary processes that he needed to know. Now, after knowing all these concepts and terms, now we move to the actual law. which is Hardy-Weinberg law. So when these kinds of all details were being discussed by the people, there was a question arise among the minds of the people that dominant alleles, when they win over the recessive alleles, over time, over generations, they should be common in population. Because they are the dominant ones. But this is not the case. Most of the population is having recessive characteristics. Okay, recessive characters are more visible. Okay, so this is very important. For example, dominant trait of widow's peak. It is not visible in many of the population. It is on a minority of population. So there are many reasons behind it. However, at that time, those reasons were not discovered. Okay, there are many reasons for this, but those reasons were not discovered. The first reasoning for this was given by Hardy and Weinberg. He was a mathematician, G.H. Hardy and W. Weinberg. They gave this particular law in 1908, possibly, if I am not wrong. Okay, Hardy-Weinberg law. Now, what they said? They said that dominant and recessive alleles remain constant in frequency. Okay, so in a population, dominant and recessive alleles remain in constant frequency if certain conditions are met. Okay, so in a population, dominant and recessive alleles remain constant if certain conditions are met regarding the population. So they gave a theory to identify whether dominant and recessive alleles or the genes and allele frequency of these alleles are changing or not. So they gave this formula, this particular law, to identify that particular question. Okay, so let us see what did they say. So first, they said that there will be a particular kind of combination of traits. For example, there could be dominant allele in the gene frequency taken to be as P. Okay, and in case of recessive they taken as Q. So, and this is just an assumption again, because they are considering only two kinds of allele in a population, only two variants of a gene. Okay, so in this case P plus Q is equal to 1, because any kind of proportion may be a 0.6 for this and 0.4 for this. 60% population having one particular trait and 40% population having another particular trait will be having a total of 1. That is 100%, nothing but. This is what they thought. And they calculated for this to find out P square plus 2PQ plus Q square is equal to 1. And you very well know this is a common Pythagoras theorem equation, and they applied this to Hardy-Weinberg law to find out the population genetic criteria to identify whether there is a change in population or not. And if you apply, it will be directly applicable, not much of a complication is there. P plus Q whole square, and P plus Q you very well know is 1. So this 1 square is nothing but 1, and P square plus 2PQ plus Q square is applied to this part. You just apply the particular values. Okay, which is 0.4 whole square, 2 into 0.6 into 0.4 is equal to 1. So what is the resultant? 0.36, 0.48, 0.16. This is the one. So leading to overall total of 1. So this kind of calculation was also plotted on a graph to show what kind of changes are there in case of population changes. For example, the P will be taken from 0 to 1. 0 to 1. And on the other hand, there will be Q taken from this side 0 to 1 on the other hand. So what will be there? And this is the expected frequency. Okay, so in this case you have, when P's value is 0 or it is approaching 1, okay, so this is nothing but we are plotting this portion, we are plotting this particular graph. Okay, so it will be like this and this. Okay, so you can see this is P square, it is a square, so it is creating a kind of parabola, and it is a Q square on the other side, the another parabola, and this is a 2PQ, which is nothing but a kind of Gaussian curve, okay, due to that particular value. So you have to understand what are these particular values. So P square is nothing but your dominant trait, and Q square is nothing but your recessive trait. Okay, and these all are homozygous. Homo because it is a square of the same value. If dominant allele is repeated in a genotype, then it is a homozygous, because having same characteristic trait repeated. On the other hand, recessive traits of a square, again homozygous, but 2pq is heterozygous because it is having both of the traits within the genotype. Okay, so this is the basic representation of this particular law, and in this law, this constancy that we talked about is called equilibrium. That means the population remains in equilibrium, the gene frequencies and allele frequencies remain in equilibrium in this case. Okay, they always remain in equilibrium according to Hardy-Weinberg law. They are not like dominant will be always over time becoming common in the population. That is not the case. Dominant will remain dominant having some proportion, and recessive will remain recessive having some proportion. If, again a big if, there are certain conditions met. Let us see the conditions. What are the conditions that lead to meeting of this particular traits and these conditions? So what are the conditions? These conditions nothing but apply on the population. Okay, so the population is basically having some specific traits. Okay, so first trait is that population should be infinitely large. Infinitely large population. Why infinitely large? Because if there is any change, that does not affect the whole population. Okay, so these are the conditions that Hardy and Weinberg gave. Second is it should be an interbreeding population. Also, all individuals equally fertile and offsprings also, they should also be fertile. Then there is another condition for the population, that no evolutionary forces apply. No evolutionary forces, which we talked about: the mutation, genetic drift, gene flow, natural selection, any kind of evolutionary force or process should not apply. It should be panmixis. Panmixis population, that means if there is any change in the population within one generation, it should be normalized again. Okay, panmixis population. Further, it is a random mating population. Random mating, because it is very important, not just evolutionary forces but also random mating. Mating pattern should not change, it should be fixed. Okay, for example, there should be no sexual selection, which generally occurs in general in nature based on color, ethnicity, or even in human populations it is about some selecting based on some characteristics. So random mating should be there. There should be no preference in the mating. So these are the major conditions that should be followed so that that particular law should apply in that case. So these are the major conditions where this particular law will follow. Okay, and we very well know that this kind of population is simply not available in reality. Okay, it is a imaginary population, it is an ideal population. Okay, so if any kind of value changes, that proportion will change, and whenever there is a change in proportion, it will be reflecting of evolution, change in the gene frequency and allele frequency. That's what we are going to test here. And finally, applications. Let us see some applications. Where do we use this particular law, and how do we what are the advantages of the law or significance? So there are few specific applications. One application is that detection of evolution. In population, if there is any evolution in population happening or not, you will be able to know. Okay, then direction of evolution in the population, which direction the evolution is happening. Okay, how do you know about this? Through two methods. Either you take the data over time period, you take a data at one particular month and you take another data at another particular month, maybe after 6 months, so that will be a twice a data in a year. So that will give you some direction of evolution. Okay, you can take different criteria, for example age groups, based on which you can see which age group is more affected by evolution. So that will show you the direction of evolution. Then you can see specific genetic alleles in population. Specific genetic alleles in population, possibly a kind of disorder, which will help in mending the population or possibly providing the population with a health policy. Okay, so very important, because you know maybe particular genetic allele could be there, like in African population there is sickle cell anemia, so you can provide some kind of benefits for them in that particular disorder. Okay, so this is very important in policy perspective. Another application is academic application. Mathematical genetics, because genetics is majorly about, in case of population you have lot of data and that data is computed to find out genetic applications, to assess the population, to find out whether what kind of changes are happening in the population, and based on that lot of studies are conducted and it will be contributing to the discipline of anthropology. Very important. Okay, and there are many other applications but not much important here. Okay, so thank you very much for this lecture.